Hello, can you hear me? Okay, it seems to be working. Nice, thank you. Good morning, everyone. My name is Flavio Leitner. I'm a software engineer working in network services team at Red Hat. And I've been playing with SDN, especially with vSwitch for the last year. So I did some experiments with Linux Bridge, vSwitch, and vSwitch integrated with DPDK, which I would like to share the results with the community. But before I start, I would like to know, please raise your hand if you know what Linux Bridge is. Okay, cool, pretty much everyone. And what about vSwitch? Oh, nice. And DPDK? Okay, half of the stage, okay. So DPDK stands for Data Path Development Kit. It's a project started by Intel, and the idea is to provide a set of libraries and drivers that you can fetch and push packets as fast as possible from the user space. We'll do some experiments with it because we are seeing a lot of impressive numbers, at least the people say about impressive numbers, but let's take a look how it performs on our common use cases. So this is the agenda for this talk. First, I will talk about the motivation, then about the testing environment, I use it. Also, how I did some traffic and hardware validation, the software stack being used, and then 3 simple use cases, forwarding packets from one port to another port, host to host, and that means using the local networking stack, and then host to VM. And I will open for question and answers. Okay, motivations. I guess, if you join DevConf in any time until now, you probably heard the word Docker. You probably heard the word container or VMs. It seems to be all about that. So, but we need to provide network connectivity to those things. If you have 2 or more containers, 2 or more VMs running on the host, or even a single one, we need to provide network for those things. And then comes the questions I've been hearing a lot in the last year. If vSwitch is faster than Linux Bridge, and I should replace that, or if vSwitch integrated with DPDK is better. I'm afraid that maybe I will not be able to answer those questions completely because, when we talk about performance, there are a lot of variables that each use case may have different requirements, so we have to adjust here and there, and you can get more performance in your case, or you can get better performance in the other case. So hardware descriptions. I have 2 server models, model Supermicro. It runs Xeon CPU, model E5-2650 version 2. It's pretty much 32 logical CPUs and 2 different sockets. But my network card is attached to socket 0, so I'm isolating everything to just one socket. 32 gigabytes of RAM, and the network card is Intel 82599. It's a dual port 10 gigabit network card. The test environment is very, very simple. The 2 servers are connected back to back, so I have the port which I call P1 connect to P1 and P0 directly to P0. So I have no switches in the middle, simply back to back. I will try to see if I can forward packets fast enough between those 2 systems using these 2 connections. All right, software stack. I'm using Fedora 21 and kernel 3.17.8-300. This is important because if you try to compile with newer kernel, the DPDK might have some issues. Compile issues that you need to fix first. But otherwise, you can use the upstream kernel, no problem. The net perf is the 260. DPDK I'm using is 1.8.0, but not using the UIO driver. I'm using the VFIO driver. Packaging for traffic generation, I'm using the packaging DPDK. This is based on DPDK 1.7.1. But since this is compiled statically into the packaging, it doesn't interfere with OVS. So OVS is linked to this DPDK, and packaging is linked to this DPDK. But packaging DPDK is running on a system, and OVS is running on another system. OVS+Switch, I got the last one from a couple of weeks ago. This is the hash from the master branch I am using. I also applied 2 patches on top of it. One is to bring because currently the OVS+Switch requires DPDK 1.7.1, but to test vhost queues, we need to bring up the requirements to this version, this DPDK version, and then apply the vhost queues patch set. I will explain more about the vhost queues patch set in the next slides. SCA Linux is off, RQ balance is off, CPU government set to performance, and C states is limited to just 1. Okay, hardware validation. How I did my hardware validation. The question is the hardware capable of pushing line height speed, or I have problems with my hardware? So what I did is I run package DPDK on both ends, on both servers, and the packet information is the smallest packet possible. So it's 64-byte frame, which is 14 bytes for MAC header, 46 to payload, plus 4 for CRC. So this is the smallest Ethernet frame possible. And this is the direction, this is the test. So I'm running package DPDK here, pushing traffic through P0 to the other side, and receiving here with the package DPDK. I can see how many packets per second it is receiving. And this is 14.88 million packets per second, or 90,999 megabits per second, which is line height speed. Then I enable the other side, pushing traffic from P1 to the other side on the P1, and I got the same result. So I'm able to push traffic from this server to this server, and these two are running now at the same time. So I'm able to push traffic from P0 to P0 on the other side, and then push traffic from P1 to the P1 on the other side at line height speed. Okay, now enabling a bidirectional traffic. So I have P0 transmitting to the other side, and P0 here transmitting to the other side as well. Now things are not that good. I mean, I am able to push traffic, but receiving only 10.57 million packets per second, or 7.1 gigabits per second. I think in the way that DPDK works, it pushes traffic using a single CPU exclusively, so the CPU is 100% busy all the time, regardless of the traffic you are pushing or receiving. This seems to be, I suppose, related to the bandwidth in the PCIe Generation 2 X8 bus, because I think I saturated the bus at this moment. Okay, L24. This is the first test. So the idea is to run the L24 here. Is an application, a DPDK sample application, which does it will use a port device as a DPDK port, will receive the packet in P0 here, and copy to sending this packet to P1. But it does change the MAC address. So receive it here using DPDK, change the MAC address, the destination MAC address, and then send through P1. This is basically the test. So traffic comes here, L2 forward, and then come back. And here I measure how many packets I am receiving. Okay, modify it. Why I need to modify it? Because I want to have a baseline, and the L2 forward is changing the destination MAC address. I don't want any CPU processing happening at this point. I just want a simple receiving here and pushing the same packet there. I don't need any changes. So I changed the L2 forward application to simply not change anything in the packet. And I was able to run at 14.87 million packets per second, almost line height speed, but it was bouncing. So even using DPDK, the line height speed is quite hard to achieve with small packet size. So what happens is that I had C-states enabled yet at this moment, and I saw the bouncing happening, but once the C-states were disabled in all CPUs, then it went to the line height speed. So you really need full power to do line height speed. Okay, let's see how Linux Bridge works in that scenario. So going back to the slide, I am running Linux Bridge here with these two ports attached to the bridge, and this one is pushing traffic to P0 and receiving the same traffic on P1. Okay, with a single flow, so I have flows down here, and here is megabits per second. With a single flow, I reach mostly 1 gigabits per second. As you add more flows, it starts to scaling up. This happens because the network cards, they receive the packet, they have the receive side scaling, which works like this. You receive a packet, and then it will apply the hash function on the packet header, and based on the result, it will map to a queue. This queue is inside of the network card, and it's mapped to a single CPU. So as you add more flows, you pretty much are mapping, you are steering the traffic to other queues, different queues, and then to different CPUs. So you are able to scale up. And we can see on the graph that this is happening, except for the 8 flows that somehow I got a sweet spot there, and the throughput was a lot better. I could see all the CPUs running about 60%. And in the other cases, I always had one CPU in 100%, and the others were pretty much idle. The explanation for having the other CPUs almost idle is that since we have these multiple queues working in parallel, and we cannot have reordering between them, if there is a hash collision, which means I have 2 flows going to the same queue, one CPU is a lot more busy than the other ones. And this causes problems in the other queues. We have to wait this busy queue to process what is in front to them, and then process the other queues next. Okay, this is many to one. This means in the previous test, it was one server talking to another server. So I have the same MAC address, same IP address, and just changing the ports. So I have 2 servers communicating between each other. What happens if we have many clients, many servers talking to just one? So I'm now changing the source MAC address. We can see it's scaling up as well, but now the sweet spot moved to 16, and it's stabilized almost at 7.5 gigabits per second. Last column here is hub. Hub is when you set aging to 0. The idea was to check if the forwarding, because Linux Bridge does the forwarding lookups in the forwarding database, when we disable aging, setting it to 0, the bridge becomes a hub, so there is no more forwarding database, but in this case it didn't help. It stays in the same. So for the throughput perspective, it doesn't help, but it helps with CPU processing. Okay, packet sizes. Let's see what happens if we increase the packet size. So here is with, this is 8 streams in parallel with 6 4-byte packet. We can see above 4 gigabits per second. And as we increase the size, we reach line height speed. So somewhere between 128 and 256, we reach line height speed. The problem is really with the small packet size. Okay, let's see Open vSwitch. It's the same explanation for the receive side scaling, works for the Open vSwitch as well, because it's the same stack for both. So you have for one single flow, you have about 1 gigabits per second, and then it increases. The same sweet spot happened with 8 flows, and this is pretty much related to how the network card works internally. But then it stops the scaling and have a bit of drop in the throughput here. I will explain more about this in the next slide. Now many to one. So many clients talk to one server. I'm changing the source MAC address and also the IP addresses. So as we increase the flow, the same thing happens. And again, the sweet spot moved to the 16 flows as the same as Linux Bridge. And the same performance drop happened with, in this case. However, notice that in the last column here, which I am enable different flows, I will explain the details later, we have a jump in the throughput. Just keep in mind, I will return to this slide. Okay, let's see packet sizes. 64 bytes with 16 streams, we have almost 4 gigabits. With 128, close to 7, and 256, we have line height speed. So pretty much the same as Linux Bridge. Somewhere between these two here, we reach line height speed. Let's see OVS plus DPDK. So OVS is now running using DPDK ports. It doesn't matter the number of flows, at least in the beginning, up to 16, we have line height speed. And this is one of the things that call attention for DPDK. We can have line height speed, close to line height speed actually, with a single flow. And with more flows, we stay at the same numbers. So it's close to line height. And this is one-to-one. Many-to-many doesn't change much because DPDK doesn't support RSS, receive side scaling at that version, so it doesn't matter much if I change the sources or not. I mean, the source MAC addresses and the source IP address, it's still the same. However, it drops down here. The same thing happened with OVS without DPDK, and now it is happening with OVS plus DPDK. Okay, packet sizes. So with 64 bytes, we have almost line height speed, and 128, we are at line height speed as well. So Linux Bridge and OVS, we are in the middle, and here with DPDK, we move that to this between these two. We can see all three together in the same graph now. So you see both together here, Linux Bridge and OVS, same here, and same here, and DPDK with a single, with a small packet size, almost at line height speed, and here already in line height speed. All right, this is the one-to-one, all three together. So in blue is the Linux Bridge coming up and scaling up to here. And in green, you can see Open vSwitch scaling up to this point, and then the performance issue happening. And DPDK having the performance issue here as well. But with single flows, it's close to the line height speed over here. Many-to-one, pretty much the same thing. Okay, I was curious to find out because I have a test I did 6 months ago with another version of OVS, And I saw the same pattern happening with the Linux Bridge and OVS. But then when we started to use more flows, Linux Bridge was spending time doing forwarding lookups in the forwarding database. But OVS doesn't work like that, so we had a better performance. And with a lot of streams in parallel, OVS matched line height speed with the same as OVS+DPDK, while Linux Bridge was spending time doing lookups in the forwarding database. This is quite strange because OVS works with flows. So I have the flexibility to do this test at least in two different ways. One is saying, telling using flows to OVS to say like this, whatever you receive in the port 1, send to port 2. And whatever you receive in port 2, send to port 1. This doesn't use it for forwarding database. It doesn't care about MAC address. And do it to the megaflow, which is a feature added not so long ago in OVS. This is cached inside of the kernel in the fast data path. So the packet process should be a lot faster than Linux Bridge. However, I can pretty much try the same thing as the Linux Bridge does by simply telling vSwitch to use the Mac Learning. So instead of doing the shortcut with using OpenFlow, I will tell, hey, whatever you receive in this port, use Mac Learning. And whatever you receive in that port, use Mac Learning. So in that way, I have to do forwarding database lookups, sort of like this. So what happens is that if running perf, I could see that the OVS was spending too much time on OVS flow stats update. Okay, so going back to the two ways to test OVS. In one case, when I was telling simply take the packet received on this port and send to the other port, I have a single flow in the data path, and all CPUs are trying to update that flow. I'm trying to update the stats on that flow. So I have 16 CPUs fighting to update a single flow. That's the bottleneck that's causing the graph to go down. Oops. To go down here. As more flows I add, more the CPUs fight to update the stats of that flow. This is due to a recent change in OVS, and I'm quite sure we can improve that a lot. So the idea is to OVS to scale scale better than what we have right now. Okay, so host to host. How this works is I have in one side the interface assigned with IP address, so I'm using the local host in the networking stack. And in the other host, I have the bridge, and then IP address assigned to this bridge. So what happens is with Linux Bridge, we can see it's scaling up. Yes, as we increase the number of bytes, and vSwitch also increasing up, but OVS+DPDK does not perform that well. You can see that with 1400, it stays over here. This is the request response test with 16 streams. We can see TCP, both Linux Bridge and OVS going high here. It's 35,000 transactions per second, and DPDK is not that good anymore. Same here with ODP. And here is TCP stream. So you can see DPDK does not perform well. Why it does not perform well? DPDK is running in user space, and the local stack is in kernel space, so we have to switch context. I have a slide next to explain this detail, but just keep in mind that there is this big gap over here. This is host to VM. Host to VM, same thing. Linux Bridge and OVS performance pretty much close to each other, scaling up, and with huge packets goes like this. And if you notice, there is no OVS DPDK numbers here. This is related to the same explanation for the data path being in user space. Here is the request response. You can see Linux Bridge and OVS working pretty close to each other. And here is let me explain you why OVS+DPDK doesn't perform that well when we are using the local network stack or with VM. So basically, OVS integrated with DPDK is running in user space. I have the packets coming in user space, and it's being processed in user space. So if I have to forward the traffic back to the network card, I remain in user space, and that's good. The performance is really well, as we could see in the first graphs. Doesn't matter how many strings. But if I am using the local stack, I'm assigning an IP address to OVS bridge, I have to jump from do the context switch between the user space to the kernel space. And this is very expensive, and we don't have any optimization for this. I mean, we are pushing packet by packet to kernel. And then if there is a reply, this reply should go back to user space and then to the network card. So it's very inefficient. That's why OVS integrated with DPDK doesn't play well if you have to use the kernel. And the same explanation is valid when we are using VMs, because VM interfaces with the KeyEmu, and KeyEmu usually creates a tap device, which is in the kernel. So what happens is that we receive the packet in user space, do the bridge processing here in user space, then we have to inject the packet in the kernel space for the tap device, which is backed by a file descriptor in user space. So we do these two context switches and then deliver to VM. The VM pushes back the packet, and we have to go all backwards here. So this is it's even more inefficient. What's being done now? I told you in the beginning of the presentation about the OVS queues and OVS vhost user. The idea is to simply take the file descriptor here and share a memory between these two. So the OVS+DPDK will put a copy in the shared memory, and KeyEmu would be able to read this packet from here and deliver to VM. This should be the fast path, but this is not working yet. At least in my environment, I couldn't make it work in time. The patches are available in the list. They are in review stage yet. They are passing through the review. Hopefully, there is a working being done in DPDK vhost library, which is scheduled for DPDK 2.0. Hopefully, it will make it. After this work with the vhost library is done, I believe it will be possible to implement OVS+DPDK with vhost user to connect these two together. Okay, questions? Did I speak too fast? Okay.
Is there anyone working upstream in the long-term future to get DPDK or something similar upstream? Or is there no chance because it's invasive?
Okay. The question was if we are working to make DPDK upstream, correct? Okay. DPDK is upstream. DPDK is a project started by Intel, and it's now upstream. It will never be, okay. DPDK runs mostly in user space, but it needs some way to tell the kernel, hey, give me access to the network card. We have some UIO drivers that expose the driver completely, and the VFIO driver, those are in the kernel already. I'm using actually the Fedora with that interface. More questions? Yes?
Are you running your test with hyper-threading enabled?
Yes, hyper-threading enabled. Any other questions?
So you said that OVS was faster because it didn't do lookups to fill because
Yes.
it was configured via flows.
Yes.
So you configured
Yeah, vSwitch allows you to add flows. So what happens inside of the bridges depend on those rules. It's like table rules. You have the matching part and the action part. So you have the flexibility to tell whatever you want. If you want to say, hey, if the packet comes from this port and have this field set and in this way, do this and that. So have this flexibility, which is not possible with Linux bridge. So I have at least two ways of testing this. One is simply telling whatever comes in this port, forward it to the other port, and do the opposite as well. So this does not imply any forwarding database lookups. I don't need to care about the MAC addresses. I don't need to care about the IP address. I just move the packets between the ports. Or I can tell the OVS to work as any other switch does with MAC learning. So for every packet received, it will have to look at the MAC address, look at the database, see where the MAC address is located in which port, and then send the packet. So we have these two options.
To use floats, you have to know beforehand what will be happening on the network, so you have to configure OVS before any packet comes in.
Yes, you can be proactive in this case. You can program it before. Or if you receive a packet that's not in the programmed flows, OVS will ask for help, let's say. It will send to the controller, and the controller will, hey, this packet should be following these rules, please update.
So what are some of the future steps for DPDK, DPDK plus OVS, about packaging, feature set, what's on the pipeline?
Yeah, for the DPDK 1.8, there is a patch called vhost queues for OVS in the review right now, and hopefully it will make the next big release of OVS, which is 2.4. And as I said earlier, there is a work being done in vhost library. This is scheduled for DPDK 2.0. After that, we hope to have the vhost user implementation, which is that ring sharing I explained before, ready for OVS as well. More questions? What OpenFlow version?
Yes.
Okay. This has been changing quite frequently. So if you take the branch master, it supports the draft of OpenFlow 1.5. Yes? Sorry, I couldn't hear you. Integrate with DPDK? Yeah, it runs inside of the guest, right? Yeah, I haven't tried actually with VirtualNet because I still need to pass the packet through from the OVS to the QEMU. So I need to go to the kernel space and then back to the user space. To then we use the VirtualNet. So VirtualNet is the next step. It does not replace that part. There is, though, the QEMU which supports a vhost, but this happens at this part here. We have a shared memory between the tap device and QEMU, and the signaling going in parallel. So it's faster than injecting the packet and using syscalls. But it helps in this case, but still you have this part here which is pretty slow. Okay. Yes.
There is a tested tool, TJAM, available on your website, the website DPDK.org. The question if you use any other tools for generating the traffic, what kind of tools? How do you measure?
Well, in this case, I'm using NetPerf and I'm using package DPDK, which allows you to program some traffic flows. You can use parallel streams, or you can use small packet sizes. You can define whatever you want. I did that mostly because for all software packet generators I tried to use using the standard Linux device, they can't put line height speed with very small packets. So it's too CPU intensive. I also have a traffic generator. I have a traffic generator, and it wasn't able to push line height speed. I hope it's in the pipeline now to get a new one. Hopefully it will be able to do so. I can do more testing with this. Yes?
One question about floats. Like, if you want to configure it, or if you use, don't use fit, but you use flows, is it driver dependent, or there is generic infrastructure in kernel that you can use flow-based like switching?
Okay. So the question was if using OVS, if the flows are hardware assisted or not, correct?
If it depends on the driver.
If it depends on the driver, no, it doesn't depend on the driver. It happens it has a generic implementation for all drivers. The only difference in those two cases is that if I'm using OVS without DPDK, I'm receiving the packet in the kernel space, and the data path stays in the user space, so the flow processing happens here, and then we either forward the packet or drop the packet. So everything stays in the user space, in the kernel space. There are a few cases where the packet needs to go to user space, but the fast path happens always here. In the OVS integrated with DPDK, the processing happens here. So the flow processing is here and here. Depends on how you are defining the data path. Okay. More questions? I think we have 1 or 2 minutes, right? 3 more minutes. More questions? About OVS, perhaps? Okay.
Question is, which workloads would work better with
Which workload? Each one is better? Yes, well, for Linux Bridge and OVS, what matters most is the number of streams because if you have a single stream, it will be mapped to a single CPU. So if that CPU is maxed out, you can't process anything more. The idea is with more streams in parallel, we can sort of steer the traffic to other CPUs as well. So most of the hardware today provides you 16 QEs. So if you have lucky to have 16 different streams mapped to 16 different CPUs, you can process a lot of more traffic than if you have just a single stream. And the other thing is packet size. If you are pushing very small packets, then the overhead is a lot more than if you have just more data associated with the packet.
But both OVS and vSwitch have the same, more or less, level of overhead.
Yes. It's pretty much the same. What makes the difference actually if you start using more things on the stack. If you add IP tables, for instance, then each packet will go to IP tables, and then there is this additional cost, and then you will start to see more. The per processing packet comes to be a little higher than without it. Okay, so it's mainly packet size and number of streams for OVS and for Linux Bridge. And packet size, though, If we look at the graphs, actually, oops, too much. No. This. So it's really small packets. Something between those two, we are already at line height speed. So 128 bytes. I mean, if you look at the data center, okay, the average packet size is probably higher than this. This is more interesting for telco companies because the mobile pattern is really small packets, and they also have this signaling control packets. I think they fit here in 64 range. Okay, I'm running out of time. Thank you very much for coming.
We will need the mic.
Oh, yeah, sure. Oops.
I did put it in the system.